Now I'm going to be explaining another important article which is called Self-Guided Contrastive Learning for BERT Sentence Representations. So this paper in 2021, and the motivation is that although BERT and its variants have reshaped the NLP landscape, it still remains unclear how best to derive sentence embeddings from such pre-trained transformers. In this work, we propose a contrastive learning method that utilizes self-guidance for improving the quality of BERT sentence representations. So our method fine-tunes BERT in a self-supervised fashion and does not rely on data augmentation and enables the usual CLS token to function as sentence vectors. We redesign the contrastive learning objective when applied to sentence representation learning. So this is my part 2 of my playlist. So as BERT mostly requires some time of adaptation to be properly applied to a task of interest, it might not be desirable to derive sentence embeddings directly from BERT without fine-tuning. So while this article attempts to alleviate this problem with typical supervised fine-tuning, we restrict ourselves to revising BERT in an unsupervised manner, meaning that our method only demands a bunch of raw sentences for training. So among possible unsupervised learning strategies, we concentrate on contrastive learning, which can inherently motivate BERT to be aware of similarities between different sentence embeddings. Considering that sentence vectors are widely used in computing the similarity of two sentences, the inductive bias introduced by contrastive learning can be helpful for BERT to work well on such tasks. The problem is that sentence-level contrastive learning usually requires data augmentation or prior knowledge and training data such as order information to make plausible, possible, positive or negative samples. We attempt to circumvent these constraints by utilizing the hidden representations of BERT, which are readily accessible as samples in the embedding space. So we aim at developing a contrastive learning method that is free from external procedures such as data augmentation. A possible solution is to leverage virtual adversarial training in the embedding space. However, there is no assurance that the semantics of a sentence embedding would remain unchanged when it is added with a random noise. As an alternative, we propose to utilize the hidden representations from BERT intermediate layers, which are conceptually guaranteed to represent two corresponding sentences. So we have two BERT, one of them is fixed, the other one you're training at. So we don't want that to move very far away from that. It's in line with the approach of continual learning, that we don't want to lose whatever we have learned. So we have two BERT, one of them is fixed, the other one is training. And then we give it to the projection head. So given B sentences in a mini batch, say for example S sub 1 and sub B, we feed each sentence into BERT fixed to compute token level hidden representation. And D here is the size of the BERT's hidden representation. And then we apply a pooling function for deriving diverse sentence level views from all layers. And finally, we choose the final view to be utilized by applying a sampling function. And we have no specific constraint in defining P and sigma, and we employ max pooling as P and uniform sampler as sigma for just simplicity. Unless something else is set. So this simple choice for the sampler implies that each sub I and k has the same importance, which is persuasive considering it is knowing that different BERT layers are specialized. So third, if we compute our sentence embedding C sub I, this is our sentence embedding for sentence sub I, and we give it to BERT and it answers it. We collect the set of computed vectors into X, and then we compute this loss, which is just the base, which is just the log of phi, and tau is the temperature hyperparameter, and F is just a projection. This F is just a projection. Head consisting of some multi-layer perceptron layers, and this G is just a cosine similarity function, and this mu here is the matching function defined like this, that if xi is equal to C sub I, and so it becomes H sub I. If x is equal to H sub I, it becomes C sub I. And the regularization we added to prevent BERT T from being too distant from BERT fixed. So as a result, the final loss is just the sum of base and the regularization. And lambda here is just the hyperparameter. So we relied on a simple variation, and so our aim is to improve C sub I with the aid of H sub I. We redefine our loss, focusing more on C sub I rather than considering C sub I and H sub I as equivalent entities. So H sub I only functions as points that C sub I is encouraged to be close to or away from, and is not deemed as targets to be optimized. And this revision naturally results in removing 4. Furthermore, we discovered that 2 is also significant for improving performance, and thus deriving this loss. And we diversify signals by allowing multiple views to guide C sub I. And we expect that this refinement, that the learning objective can provide more precise and fruitful training signals by considering additional samples being provided with. And the final form of our optimized loss is just this one, that we add the regularization loss with this lambda hyperparameter. So they evaluate models on 7 data sets, and they contain pairs of 2 sentences whose similarity scores are labeled from 0 to 5. And the relevance between the gold annotations and the scores predicted by the sentence vectors is measured in this correlation. And this CLS is just the CLS vector for the last layer of BERT. And this mean pooling conducts mean pooling on the last layer of BERT and use the output as a sentence embedding.